That one's easy to play on guitar. Maybe not drums. All right, so what we'll do is, I think I have some notes this week, but I think what I want to do also is go over the problem that I recorded. I don't know if anybody had a chance to look at it, but it was that in-class assignment where you didn't get to that problem with differential inequalities and what the y is. I do want you to see that. I did put something on the T like that, so I feel like I want to do that in class so you can fully see that. Maybe I'll do that Friday, so I fully have that done well because I was rushing through it during Projects Day week. T is starting to be developed. I can tell you that entirety of quiz 2 is on there. So if you want to start studying, that's and the quiz keys are online on Canvas. So you can pull them down and actually look at them and study off of them. Ask me any questions you want. You actually can raise grades on the T. We'll give you the template as soon as Dr. Groves puts in her questions. We'll send you the template just like before. We'll strip the identity of the actual question, but you'll see what the type of questions are. So it's going to verbatim be that exact thing. So Patrick had asked a really good question, and I think with 2 instructors teaching this, you can kind of feel all over the place. So just to tie everything together, what we're doing, so you can kind of get a feel for what the point was for everything. So this is just tying it all together. It's a strange thing. A class should have a point. You spend all semester in a class. You should come out of that class somebody different than you walked into the class. I always believe that. And then whatever you do in class as an instructor should be to reach that point. The point of this class is what we're doing right now. And that was not just the point of this class, it's the point of almost all your education was coming to this point where you're going to be greased up to be an engineer. That's what our education system was set up for. So this is the kind of math that you do as an engineer. We've come a long way. We're talking about math history too, because I actually know the people who ran punch cards. I interacted with them. They were my advisors, or I actually met Edward Lorenz. I'm going to bring that in for you guys so you can see it. That was the era that this kind of math all started in. That's when it permeated our schools. So where did we start? We started out with Jedi Master. We started with linear 1D models. In fact, really, they tried to make it general, but you really started out with something like this, or something like this. That's where we started. In fact, I told you that's actually the most important equation that underlies the theory. And then you use methods. Integrating factor. Separation of variables. And they were like, if you look back in your notes, these were softball things. They were easy things back in the beginning. The point of that is, I think, it's easy to eliminate this now because you can just go on Mathematica. And I don't even go to DSolve. I go to NDSolve, the numerical one, because I don't even want to think about whether it's separable or if I can find a closed form solution. I just want to see what the solution looks like. So I don't want to waste my time doing both and finding out it can't be solved. But the point of this is that I learned it to become who I am, and somewhere along the lines, I'm doing it without any notes. That means I've done it again and again. So to eliminate it from a class like this is probably not a good thing, even though it's not a useful tool anymore. Somewhere along the lines, I'm doing it. So I'm not sure where, but if I have it committed to my muscle memory, then I'm using it somewhere above and beyond just teaching a class. The second thing is you went to linear multidimensional models. Something like this. What do you think, out of this section, what do you think was the most important thing that you learned, that kept revisiting itself as you went along? Like if you had to write a final right now, what do you think or next year's class? Let's say Clown came into next year's class to teach next year's class. Clown did come to this one, but next year's class. What would you expect the students to know after they walked out from that first section?
I think integrated factor came back a lot.
Yeah, I think so too. Yeah. Yeah, even here it comes back because we have like the general solutions integrating factor. Separation of variables, yeah, maybe you'd have to look back at your notes on that one. I haven't forgot it, but it's, I think I've used this one much more. So you can expect that to be on the final. It's going to be there. Next, you went to here. What do you think you walked away from here that you kept using after this section was out? Wronskian? Yeah, we did do Wronskian. I don't know if Dr. Gross did Wronskian again. Again and again and again. What'd you do with that matrix? Eigenvalues and to write down the general solution and then later to characterize what's going to happen to the solution long term without use. A friend of mine from Venezuela used to talk very slow. She said, if you know the eigenvalues, you know everything. So this is the part that was most important here was eigenvalues for general solution. And stability. In all these cases, if they came out to be complex eigenvalues that had a real part, you looked at the real part, and if the real part was bigger than 0, then it ended up being unstable, and then you had all these cases that you went down. So that's really important. If you're going to I would suggest if you're going to study for this, since you're allowed to have whatever you want on it, make note cards out so you can pull them up quickly. Don't come in dry and think I've got everything in front of me. That's not going to work because you have limited time. So you want everything to be drawn out and what's most important. Make a little set of note cards like what happens with each of these cases. So you can pull it out in front of you and have it to look at. That's what I would do. And then you also started drawing phase portraits. You kind of did that with one-dimensional, but that's kind of dumb. It's one-dimensional. To see what the behavior of the solution is in 2D. These are only 2Ds that you did that for. And then you learned about special solutions. In fact, you did an integrating factor in multiple dimensions. Something like that. Did this. But that's actually all prepping you for this final piece that we're doing now. It's the nonlinear stuff. Those are the equations that govern the weather, the atmosphere. Those are the equations where we build planes from. Those are the equations that we look at ocean flows. All of those things, much more than that. Differential equations are used everywhere. And that's why the education system was set up that way, is to get all students ready to do differential equations and get to this last block. So that's the third thing. All right, so the real stuff is right here, number 3. Okay, you got a nonlinear model. You have no idea what the solutions look like. Probably it's unpleasant to look at. It might be multidimensional. What would you do? Let's see if you learned something from this class. That's literally what you're going to be presented with in the real world. No one's going to give you y prime equals ay and ask you to solve that.
You make the nonlinear thing seem linear.
That's one thing you could do. And you linearize it around what?
0, 0.
Why 0, 0?
Because you can shift it if it's anything else.
And what's the anything else that you might want to have it at? Where do you want to characterize equilibrium? So you characterize around the equilibrium. That's used to be what they used to do because they had punch cards. I'm not poisoning you by telling you this is the first thing I do. I got a nonlinear model. What does Dr. T do? I would look at the solutions. put it on Mathematica. That's what I would do. In fact, if I don't remember the command, I would just go Google search, find me a differential equation solver, and then I'd put it in there and see what the solutions look like. Because I can today. And I told you that surprise on that engineer's face when I said, I can code your model. I just put Runge Kutta 4 in Visual Basic, push this button, and it will simulate your model inside this in Excel. And I think I have his email, so he was floored, because before, in the old days, he had to put punch cards in and these big computers and wait and then see one solution, then go run it again to see another initial condition. So I think the first thing I would do is use numerical methods. You learned Euler's, but I told you Runge Kutta, order 4. Most models. There is these set of models. I took a course on stiff differential equations. They just rise too fast. And so, it's not going to work for every model, but it works for most models. And that's what Mathematica is coded up for. If you put ND-solve, that's what it does. Why do you think you learned Euler's if it doesn't work for a lot of things? Why would you ever show someone Euler's method? It's much easier to do by hand. It's easier to get. Runge Kutta, if you started off teaching Runge Kutta, it doesn't make sense right away. So Euler's makes sense, what you're doing. From Euler's, you can jump off of that and explain Runge Kutta. But if you just started with Runge Kutta and a multidimensional Taylor series, that would be a hard place to start. So that's why we do Euler's. You can guarantee something on this is on the team. And then you also do, Euler gives you the idea. It's easier to code up. So once you code that up, in fact, Sarah, that's how she did it. She coded up Euler's first, made sure it worked, and then ran Runge Kutta. It's easier to do. And then all numerical methods require sniff checks. So in the old days, before they put their punch cards out, they had to have a sniff check to make sure they know what the solution's supposed to look like. So when they get the stuff back, if they have a bug or if something's wrong, they'll know something is wrong because they did the analytical stuff first. That's why the analytical stuff is beat over your head. Today, I would suggest you run straight to the computer, run that thing, and then look at it and say, does it make sense to me using analytical methods? So you have to check it, because all of these things are approximations. They may miss an asymptote. Like they don't do what, in fact, that's the problem I gave you in the in-class assignment. There's an asymptote. And so it freaks out, the numerical methods do, right by the asymptote. We also taught you analytical methods, which is the sniff checks. Our linearization around equilibrium. You have to linearize around a point because not the whole thing is linear. And what they did is they just told you that the origin is the place to look at. I'm super lazy. I don't want to shift everything. The reason they did the origin is because they didn't have Mathematica to do the algebra for them. I just keep it right at that equilibrium point and plug that into the Jacobian. There's reasons why they did it that way in the past, because they wanted to make all that computation. They did computations by hand. And then you evaluate your solution. But the analytics is really hard. I actually talked to a company, and I'm going to stay here forever, so I was putting my feelers out there. And they were really worried about the fact that I write papers, because in papers, everything has to be perfect. And so all the analytical work for a differential equation has to be there. I expect it to be. If I'm reviewing something and they have a differential equation, I expect the analytical work to be in there. But for a company, you just need the answer. And so they were worried that I will always go back and do these things and be tedious about it. But I know the first thing I do is I do that. And that I know the answer then, or I know what the answer I think is supposed to look like. Okay, that's pretty much it. So this week, it's a lot of computation, but I would like to hold that with you guys because that's a lot of what differential equations is. In math, you have to be either able to do three things actually. You have to be able to do a lot of nasty computations, like an engineer. You're above an engineer because you have to do some theoretical things. If you're a math sci major, you have to take real analysis. If you're an OR major, you have to take 476. So we take these courses that engineers don't take. And then we also have to be able to code just like a computer science major. So kind of the mutt of all these three different areas. So today we're going to compute.